Now, I would like to embark in earnest in the calculation of this electric field. Now, before we embark on any calculation, we always mentally want to review our options. And notice that we have two different options that we can go for calculating electric fields. We've got this trig option and the Cartesian form option. Now, the trig option, as you see, is pretty much the same thing as computing the force on charge capital Q. We had previously done this using the trigonometric form. So if I went the trig option, I'd be pretty much just repeating what I had done in the previous lecture, and we wouldn't learn anything particularly new. I do encourage that for you, though, as an exercise at home to practice calculating electric fields. So I'd rather actually calculate things with the Cartesian form so that we get to see how that works and get a sense for when that might be our most convenient option. And as we're going to see here, it actually is. That is because we know the Cartesian coordinates of our various charges, and so everything is kind of given to us already. So this is going to be much more convenient for us in this case. The trig form would have been more convenient if, for example, we were given some of the angles in this problem. Now, as we go through this calculation, the Cartesian form is definitely the most convenient option. You will see it's a bit less grungy in this case than the trig form. It's significantly less grungy, I would say. On the other hand, because it's saving us a lot of grunge, you can imagine there's a little bit more mathematical sophistication associated with this method. And so we're going to have to try to remember a little bit more advanced mathematics, a little bit more of our vector algebra. So this will be a good review for us for our vector algebra, while at the same time it will show us a new way for calculating electric fields, which can be much more convenient and less error prone once you've kind of reviewed and refreshed your vectors. So let's go ahead then and jump into calculating this using our Cartesian form for the electric field. So now we're going to begin what's going to turn into a bit of a grungy calculation, but it's worth doing. Now, for any of these calculations, what I highly recommend is the first line that we write down should simply be the generic formula that we're trying to implement. We're basically just going to copy down the generic formula, because you can't go wrong with the basic formula. So this, at least, I know is right. I've got Coulomb's constant, my charge, the difference vector between where I'm calculating the field and the particular charge, which is the source of the field. It's then divided by the magnitude of that vector to the third power. Again, don't freak out. We know it goes like 1 over r squared, but remember we've got a factor of r here in the numerator. So this is the appropriate form, the Cartesian form for the electric field. Now, this is the part where most of the errors will come in. Most errors committed in physics really are going from the general formula, which we know is a physical law, to where we begin to interpret the specific terms in that formula in terms of the physical situation that's presented to us. So we have to map from the physics into the general mathematical form. We need to be very careful what each of these terms mean. So let's go through this slowly. I have a sum. That means I should write down actually a series of terms. I'll be organized, and I'll start with the n equals 1 term. So I better label my charges. Let's call this charge over here number 1. I'll call the charge on the left number 2. So I'm going to write down this expression now for n equals 1. So in that n equals 1 term, I have, of course, Coulomb's constant. Then I will have a numerator and a denominator. In the numerator, I have charge q sub 1 because n equals 1. But charge 1, actually, the name that I've given that charge in the specific problem that I'm dealing with actually is q. So that will just be a q. I can open up my parentheses now. The first vector we have, r, notice, represents the location where I am calculating the electric field. So that vector refers to this vector that takes me from the origin to that location that's a distance z above the x-axis. To write this as a vector, remember what a vector is. A vector is an instruction. A position vector in particular is an instruction of how to get from the origin to the point of interest. In this case, the instruction would be go a distance z along the z-axis, or more specifically in vector language, go a distance z in the k-hat direction. And the way we write such instructions in vector language is we give the magnitude, or the distance, z, and then we write down the direction, the k-hat direction. Very good. So that translated the vector r. The next term, I have a subtraction that I should include, and then I have to subtract off the location of my charge. This is the charge whose charge I just written down. This is the charge that is making the present contribution to the overall total electric field. So I need to put the location for here for charge number 1. This charge sits relative to the origin along this position vector. The instruction now is to go a distance capital R, but the distance that I travel is now in the x direction, otherwise known as the I-hat direction. So I go a distance r in the I-hat direction. And I then can close my parentheses. Finally, I have the denominator. But in this particular formula, the denominator is relatively easy to write down. It's just the magnitude of the vector that I just wrote in the parentheses, and then I cube it. So I'll take the magnitude, and the vector that I had just written in the parentheses was just z times k hat, and then minus r times I hat. I take the magnitude of that, and I cube it. Whew. All right, we got the first contribution down. Now we might be tempted to start to simplify this, but I like to put off all simplifications until after I've completed very carefully this critical translation stage. So let's go then to the next term in my sum. There are only 2 charges, so there's only 2 terms. Each term has Coulomb's constant. Again, there's numerator and denominator. I have to put charge Q2 now because n equals 2, but charge number 2 has a charge of just Q again. So that's Q. I then can open up my parentheses. The first vector is the location where I'm calculating the field, just like it was before, and I already have the result for that, so that's z times k hat. And then I have to go minus, and now I have to write down the location of charge number n equals 2. That charge is over on this side of the line, and its position vector is then the instruction of how to get from the origin here over to that point. That would be this displacement vector. And the instruction that corresponds to then is to go a distance r, but in the minus I hat direction. So I think with all these minus signs, I'd better open up a parenthesis. So I'm going to open up a parenthesis for writing down this r sub 2 vector. So this, what goes in here, will be actually r sub 2. And then I better remember, of course, the real closed parentheses that appears in the formula. Now, that r sub 2 vector I just said is to go a distance capital R, but the direction I go in from the origin is in the minus I hat direction. So there's minus I hat, like so. Now, the last bit is I have to divide by the magnitude of the vector here that I just wrote down. So let me put the magnitude. Of course, it's the magnitude cubed. And now I need to copy my vector. So I'll have zk hat. And okay, now here maybe I'll break my rule a little bit. I guess I'm not really in the mood to write all this crazy number of parentheses. Look, we know when we subtract off the minus of something that these 2 minus signs are going to cancel out, right? So I can simply write this as plus. So the vector that goes in here is actually plus r times I hat. Now when I made this mathematical manipulation, notice that I treated this vector I hat just as though it were any standard variable. In fact, for nearly all mathematical operations, and we'll see many examples of this coming up, this vector notation is very useful because you can treat the vectors I hat, k hat, j hat, you can treat them almost just like normal variables. If you're not sure when you can or where you can't do that, or if these manipulations that I'm showing you seem unfamiliar, I highly recommend that you might ask your TA to review them for you in section. Okay, so I've now gotten the basic translation down. The next step is to start to make simplifications. And in fact, I already made one simplification handling the sign. Let's see what else I can do to simplify things. Well, one thing I notice is that I can compute the magnitudes of these vectors. Recall that the magnitude of a vector is the same thing as its length. And the length of this vector by the Pythagorean theorem is the square root of the sum of the squares of the components of the vector. So this would just be then square root of z squared plus, now the other component here is minus r, quantity squared. But maybe I'm being a little extra pedantic because we know that when we take minus r and we square it, that's the same thing as just r squared. The minus sign goes away when you square. But this is nice though, because notice when I look at the other denominator, of course, this square root has to be cubed in the end. That's interesting. Here comes again our favorite 3/2 power. Anyway, back to the magnitude of this one. Notice it's going to be exactly the same thing as what I had just written down. This will be square root then of z squared plus capital R squared. So this then is interesting. I've got a lot of common factors between these two terms, kc and q, and they both have this same denominator, my favorite sum of squares to the 3/2 power. Given that, we know how to simplify things. Remember, neatness counts, and you always want to make as much algebraic simplification as possible. So what we would do when we have common factors is to factor them out, to use the distributive property backwards. So in the numerator, I've got Coulomb's constant times q, and in the denominator of both terms, I've got root z squared. Oh, let's get this to the 3/2 power now, right? I've got this, in both cases I have this square root, but it ends up being cubed. And that means I'm taking my original quantity, z squared plus r squared, I'm square rooting it, which is raising it to the 1/2 power, and then I cube that, which multiplies the 1/2, so this comes to the 3/2 power, which is very nice. I've now written down all of the common factors. In the distributive property, then I need to write down the remaining pieces inside parentheses. Now, this is a fairly long expression that I'm dealing with, and over the years I've found a number of tricks to avoid making simple little mistakes. Even though I've been doing this for many years, I still like to do this. I'd like to circle all the terms that I've used up as I go from one complicated line to another. So I've used up this factor, kq, the square root thing, and the cubed. We've taken care of that in this term, and we've taken care of the same set of factors here in the other term. So we can see that is what's left to write down is this piece plus this piece. So let me write that. So starting with the first one, I've got z times k hat, then minus cap r times I hat. That completes the first one. Plus then the second one will give me plus zk hat. And the last term on that line is the plus ri hat. And I may close my parentheses. And now we see we have even further simplifications we can make. Something very nice is happening here. Notice that my minus ri hat cancels my plus ri hat. So these two terms will cancel. And then the other two terms that are left are identical. I'm adding the same thing to itself. So when I add those, I just get twice either term, 2z times k hat. So my final result, notice, simply points in the k hat direction. The result is up. This is great because actually our guess was that the electric field should point up. So I can put a check mark there. Our guess was correct. Well, we've got this now to the point where we can make our final simplification, just kind of get everything in a nice standard form. So let me try to rewrite our result neatly. The electric field at location R, finally, after all this hard work, is equal to Coulomb's constant. And then I have a numerator. And in the numerator, I already put the Coulomb's constant. What's left is I've got Q times 2. So I like to write that down as 2Q, actually. It's kind of fitting because I've got two charges Q. So I like to lump those together. And then what was left over in the numerator was Z times K hat. This is interesting. And then in the denominator, I have my favorite factor, which is also interesting, Z squared plus R squared to the 3/2. And why I'm getting so interested all of a sudden is because we had, here, let me try to put a nice box around this. You know, your TAs always appreciate having nice boxes on the final results. Why I'm getting so excited about this is we had a guess, and I want to see how close this gets us to our guess. So let's go back up to our guess. Our guess was that the electric field, I can almost get them on the same screen. Our guess was that it would be Coulomb's constant, which is what's sitting down here, times 2qz, here it's k hat, and here I can see, yep, it's a k hat, and then divided by my denominator, r squared plus z squared to the 3/2, and I've got, I've just written in the other order, I guess, z squared plus r squared to the 3/2. It's the same thing, right? Our guess worked out. So our guess was computed in the trig form, and here we've computed this in the Cartesian form, and the fact that they line up teaches us that those two forms are equivalent. The neat thing, though, is if you look at the derivation I've done here, is you'll notice there was absolutely no trigonometry to worry about, no adjacent sides and corresponding angles at all to think about. It was a fairly straightforward, again, a little involved, and you have to kind of, brush up on your vectors and get a little more comfortable with your vectors, but I think you'll see this is much more straightforward than having to work through a lot of trigonometry. So I highly recommend this. It turned out that it was very convenient for us simply because we knew all of the coordinates that would go in, so we knew the components of all of our vectors. That's why I like to call this the Cartesian form. It's most handy, in fact, when you've got those Cartesian components. So, just to wrap up, I would just like to say this is awesome the way this thing worked out. I think it's worth celebrating, and the way I like to celebrate is to use a special symbol here which indicates that, in fact, we have a happy professor because the expression worked out perfectly on the blackboard without me making any of, typical silly mistakes that I might make.